Hello friends, welcome to Math Solution Academy. Now we talk about linear algebra. These are important topics for any PhD entrance exam. So prepare these topics very carefully and very seriously. So now we solve a problem which is an problem in GATE 2017. The problem says that given two n cross n matrix A and B with entries in C, consider the following statements. The statements are: if A and B have the same minimal polynomial, then A is similar to B. The second statement is: if A has n distinct eigenvalues, then there exists U belongs to Cn. That means U is an n cross on column vector such that U, A, U, A square U dot 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 A to the power n minus U are linearly independent. Then the question is, which of these above statements hold true? The first option is both P and Q. Second option is only P. Third option is only Q. And the last option is neither P nor Q. So we try to solve this problem. So go to first statement. The first statement is if if A and B have the same minimal polynomial, then A is similar to B. Say suppose A is an n cross n matrix and B is also an n cross n matrix. So let x into x minus 1 or say it 4 cross 4 matrix n equal to 4, because n cross n is large, so particularly we take here n equal to 4. Take n equal to 4. So A4 and B4 are two matrix, and let x into x minus 1 are minimal polynomial minimal polynomial both A and B. So these are minimal polynomial of both A and B. And let x square x minus 1 whole square is characteristic equations of A, and x into x minus 1 whole cube to 0 is an characteristic equation of B. Then the matrix A looks like 0 0 0 0 0 0 0 0 0 0 1 0 0 0 0 1, and the matrix B looks like 0 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. And clearly A and B are not similar, because the eigenvalues of A matrix is 0 and 1, each with algebraic multiplicity 2, and B is a matrix whose eigenvalues is 0 with multiplicity 1 and other is 1 with algebraic multiplicity 3. So these two matrices are not similar. So the statement if P and Q have the same minimal polynomial, then A is similar to B is false statement. Now we check the statement Q. Here let if we take U be an eigen vector, then eigenvector, then eigenvectors corresponding to eigenvalue lambda 1 corresponding to eigenvalue lambda 1, then AU equal to lambda 1 U, and in that case AU This is not linearly independent, this is linearly dependent, because u is a scalar multiple of au. So this is not in that case linearly. And if n equal to 2, if we take n equal to 2, so we prove that au is linearly independent. Now we choose u belongs to u equal to u1 u2 belongs to C2 such that for all ui is not equal to 0. So we show that this is linearly independent. So we take an equations of this, and this is, and we want to prove it that C1 C2 equal to 0, and this is C1 u1 u2, and this is C2 u1 u2, and a into this. And now friends, since a has n distinct eigen values, so a is diagonalizable, and a is looks like lambda 1 0 0 lambda 2, where lambda 1 and lambda 2 are eigenvalues of a, and these are distinct, and lambda 1 not equal to lambda 2, since this is diagonalizable and the eigenvalue go to the diagonal element. So, and this is C1 u1 u2, and this is C2 into lambda 1 u1 lambda 2 u2, and this is 0, and this imply C1 u1 plus C2 lambda 1 u1 equal to 0, and C2 u2 plus C2 lambda 2 u2 equal to 0, and this imply, and from here we called C1 plus lambda 1 C2 equal to 0, and from here u2 equal to C2 plus lambda 2 u2 equal to 0, and from these two we read lambda 1 C2 equal to 0, and C2 lambda 2 C2 is equal to 0, since each u1 and u2 not equal to 0, and these are homogeneous equations, and the determinant of these equations becomes 1 lambda 1 1 lambda 2, and this is lambda 2 minus lambda 1, and this is not equal to 0, this is lambda 2 not equal to lambda 1, and these are homogeneous equations and determinant not equal to 0. So from there we tell that this is equal to 0 by Cramer's rule. So by Cramer's rule we say from here and here we say this is 0. So we prove it that UAU is linearly independent. If we take n equal to 3, then similarly we prove that AU a square U is linearly independent. And here if we take n equal to 3, then A is an 3 cross 3 matrix, and there are 3 distinct eigenvalues, and say it lambda 1 lambda 2 lambda 3, and A, and in that case A is 0 0 0 lambda 2 0 and 0 0 lambda 3, and we want to prove that this is linearly independent. So we take an equation C2 AU plus C3 square U equal to 0, and this imply C1 U1 U2 U3 C2 of lambda 1 U lambda 2 U2 and lambda 3 U3, and similarly C3 into A square means lambda square lambda 2 square lambda 3 square, So lambda 1 square u1, lambda 2 square u2, and lambda 3 square u3. This is 0, and 0 became 0 means 0 0 0. 0 means 0 vector. Here this is 0 vector. So from here we say that c1 u1 plus c2 lambda 1 u1 plus c3 lambda 1 square u1 equal to 0, and from second c1 u2 plus c2 lambda 2 u2 plus c3 lambda 2 square u2 0, and c1 u3 c2 lambda 2 u3 and c3 lambda 3 square u3 equal to 0. And since each u1 u2 u3, since u1 u2 u3 not equal to 0, so from here we can read c1 lambda 1 c3 lambda 1 square equal to 0, c1 c2 lambda 2 c3 lambda 2 square equal to 0, and here c1 c2 lambda 3 c3 lambda 3 square equal to 0. And from here we find an coefficient matrix 1 lambda 1 lambda square 1 lambda 2 square 1 lambda 3 square. Now we find the determinant of this matrix. Now the determinant becomes 1 lambda 1 square 1 lambda 2 square 1 lambda 3 square, and all of you find the determinant, and the determinant is directly I read the determinant, and the determinant is lambda 1 lambda 2 lambda 3 and lambda 3 lambda 1, and this is not equal to 0 since lambda 1 not equal to lambda 2 not equal to lambda 3. So this is not equal to 0. So by Cramer's rule, c1 equal to c2 equal to c3 equal to 0. So a square u. So if we take here n equal to, so if we take here n equal to m, then u equal to u1 dot um belongs to cm, and we want to prove that au dot a to the power m minus 1 u is linearly independent. So we can take an relation and equations c2 au dot cm a to the power m minus 1 u is equal to 0, and this is similar for other two cases, and this becomes c1 of u1 dot um, and this is, and in that case the matrix A has m distinct eigenvalue lambda 1 lambda 2 dot lambda, so this matrix can be written as 0 0 dot 0 0 lambda 2 0, and this is lambda m, and the remaining other 0, and so in that case c2 lambda 1 u1 dot lambda m um, and this is cm lambda 1 to the power m u1 lambda m to the power m minus 1 um, and this is 0. So in that case the coefficient matrix becomes 1 lambda 1 dot lambda 1 to the power m minus 1 lambda 2 dot lambda 2 to the power m minus 1, and this becomes 1 lambda m dot lambda m to the power m minus 1, and the determinant, and these are coefficient matrix corresponding to this relations, and the determinant of these maps is equal to the product of lambda I lambda j, where I and j belongs to 1 to m. And friends, you prove yourself that this is an m into C2 and the number of product is m into C2, because the number of product is m into m C2, combination C2, because you take two eigenvalue lambda 1 lambda 2 and take it difference. So from m distinct eigenvalue you take MC2 MC2 in this type of product, and since each lambda I not equal to lambda j, so date of this matrix and say it matrix is C, and this is not equal to 0 where C is this matrix. So by Cramer's rule, C1 C2 dot Cm is also 0, and in that and for this reason AU dot a to the power m minus 1 u is linearly independent when we choose u equal to u1 dot um, and for each and for the choice of u1 u2 um such that for all ui not equal to 0 this is linearly independent, and you easily choose this and column vector in Cm. So the options here is q is true. So the statement q is true and p is false statement. So in that case the options b is true and the remaining others are false. And carefully see the problem and you learn how I solve the problem. Thank you.